I'm Toshiyuki, member of the RIKEN R-CCS, and today I just focusing on the sort of theoretical and the numerical part for how you improve the sort of calculation and solving the sort of eigenvalue problem, or in other words, or some physicists you say that the diagonalization of the sort of some matrix. Okay, so I had several experience with the collaboration with the sort of material or the material science community. So this was sort of the title page which was presented at almost 20 years ago, SC 2005. So fortunately, so this was sort of nominated as the Golden Bell finalists. Unfortunately, so we couldn't win the sort of the award, but so it was sort of very sort of honorable sort of mention to the sort of this HPC community with solving a sort of very huge problem on the sort of R simulator. So R simulator was sort of the vector supercomputer systems, which was the sort of number one fastest in the between the 2002 to 2004. Okay, so we had also the similar sort of the approach to solve sort of material anybody problem, quantum anybody problem with using the sort of R simulator. But so the main part, so this sort of project was the diagonalization. So how solve the sort of the ground state, so the smallest sort of eigenvalue and the sort of eigenvector with the sort of very huge size of the sort of Hamiltonian matrix. So the target problem was such kind of sort of the superconductor. Superconductor, the behavior. So when the sort of or the temperature was sort of is sort of almost sort of zero. Yeah. So okay. So you can see this. Yes, this kind of sort of layers sort of structure. So oxide oxide material. So that's something the layers sort of the materials. It showed sort of sometimes the sort of very high temperatures conducting the behavior, and also if we do the sort of change the sort of some materials, so that we can so simulate the sort of some another sort of physical sort of how to say property like sort of superfluidity or something. So but also so last speaker, so they say that sort of this is a sort of also the map to the sort of anybody sort of the problem. So regularly sort of map to such a sort of very the regular sort of 2D mesh and also 2D grid. So we simplify the sort of all the physical problem onto the sort of the how to say so something a sort of very simple model on, or we can simulate or solve sort of all the supercomputer current system. But also the government equations, so that was sort of yes like that. So eigenvalue problem like this. Okay, so this is also similar things. Okay, so my current works in the sort of R-CCS, this is sort of developing and sort of maintaining the sort of very huge or the high performance eigenvalue solver. But sort of historically, sort of my background is as a dense linear algebra. So the eigenvalue solver, so it solves sort of very huge, but so the dense eigen problems. So yes, this development, so it's started almost 20 years ago, and so when I started, so how to say started all the development of the maintaining a sort of eigensolver under the K and the Fugaku. So we had these 8 applications collaborations. So these are mainly all the Japanese material science community codes, but are so now we have international collaboration which uses my eigensolver their application code. Okay, so very early challenging at the supercomputer system, so almost 20 years ago. So okay, so this the picture. So this is a R simulator, vector supercomputer, so which was installed at the Yokohama. I forgot the institution name. So not JAXA. But anyway, okay. So one of the supercomputer center Japan, so it installed this system, and many Japanese users try to access, but unfortunately at the time, so we couldn't access this remotely. So the scientists need to visit the computer center and on-site, and use the local terminal to upload the program onto this system. Okay, so we have we hired the operators who work at the on-site Archimedes Center. So we run several benchmark for the material science code. So this is just one result which we were able to run the hugest as possible as we could. So the matrix size was almost 400,000 dimension. So the system it shows only 50 teraflops. At the moment, 50 teraflops is only we can obtain a single GPU card. But 20 years ago, we needed such a very huge facility to get to run such a high performance. Okay, so the time, we spent almost 3 hours to solve 400,000 dimensions eigenvalue computation. Okay, so similar, the simulation is only need a single GPU card at the moment. Okay, so this is the fact, almost 20 years ago, the historical fact. And okay, but now we are operating the Fugaku system. 10 years ago or so, we had K computers, and now Fugaku, and this year, we initiated the next Fugaku Next, the project. We expect the system architecture will be the CPU and the GPU, hybrid system. But Fugaku K, we are having a very homogeneous, only CPU interconnected, almost 50, I forgot, 150,000 CPU cores. Also, they are CPU nodes are interconnected to one system, single system. So this is a very huge system, and so of course we need to introduce the very specific highly optimized the mathematical software to solve if you want to solve the very huge eigen problem. So historically, we have developed our HPC community, numerical linear algebra community. So we developed these software packages for solving the eigenvalue problem. So iSpark. It was very very classical, and I think it is published by the book. There was no internet interconnection internet and the network service. So the software was provided by the one booklet. So we don't have any method way to the copy the program onto the memory. So we need to type the read and read a book and type onto the computer system. But also layback. So okay, thanks to the some network empowered we can access the internet, so layback and next to the scalarback. They are fully distributed, and easy to access and download from the computer site. So it is we can use the open source, which is has been developed very reliable. So the layback scalarback. So I think almost more than 200 or almost thousands of the numerical or the HPC scientists and engineers contribute to the development. So they are very reliable software. I think layback scalarback, they are still keep the position of the the standard, so de facto standard of the numerical software. I think you can find these software on anywhere in the supercomputer or the data centers. Okay, so algorithms. So we have several the historical change. So according to the architecture change. So because the iceberg and the layback, they are mainly are intended to develop or the purpose of running around on the sequential system. So just only the single CPU or the single node system. The scalarback was just intended to extend the same algorithm and the same user interface to the distributed or the interconnected parallel system. But that's the L4 and other modern numerical libraries. So they are also extended to the current supercomputer system. Last session, some students gave us the question. So whether we have parallelize or utilize the GPU for the computational resource. So of course, numerical library. So we are trying to adapt to the system, the upgrade from the very homogeneous CPU to the hybrid of the CPU and the GPU. So they are very trend in the current numerical libraries. Okay, so but my center. So here, we have only the homogeneous CPU only system. So my library and my software it is not supporting the GPU, only the CPU hybrid, CPU interconnected parallel computation. Okay, so I think you are very interested in how large or how fast the numerical library. So it provide or it offers the better performance. So this is this is a strong scaling performance results, benchmark results run on the Fugaku system. So matrix size, you see the capital N. So let's refer to the matrix size. So current CPU, the current the modern supercomputer system, it has a sort of very large memory space, the capacity. So when we run the sort of small benchmark, but small needs a sort of such kind of sort of large matrix dimension. So at least sort of we need a sort of 100,000 for the sort of benchmarking. So otherwise, sort of we cannot obtain the sort of good parallel efficiency. Of course, it runs so very fast, but to confirm the sort of the parallel efficiency, so we need such a sort of large benchmark for the sort of performance confirmation. Okay, so and we choose a sort of n, so 65,000. So which line? This line. Okay, so yes, it's a solid line. So this is sort of smallest, but also the 65,000 so matrix size benchmarking case. So if we run the benchmark with the 64 computational nodes, so I think a single node of Fugaku system, it shows a sort of 3 teraflops. Is it correct? 3 teraflops a single node, single CPU. Yes, like that. I don't actually remember so the single node performance, but 64 Fugaku computational node. So we can run such kind of sort of benchmark with less than the 100 seconds. So it's approximately sort of 1 minute. So I don't know. You feel that so this is a reasonable or it runs so very fast? But for me, this is so very fantastic, so very excellent performance. And then, so if we double the matrix size, so this line, we need also 300 seconds. So only so 2 times, 3 times increments or solving the sort of this benchmarking. Also, 200,000. Yes, this line. Because the sort of memory capacity is small, is limited, so we need at least a sort of 100 CPU computation of Fugaku node. But we need only sort of 1,000 seconds. 200,000, so it is a huge case. If you have a sort of only sort of small cluster, so we need to treat the sort of matrix as a sort of sparse matrix, or sparse matrix solver is required to deal with such as matrix size. But supercomputers like the Fugaku, the homogeneous and the sort of very massive system. So this size or these matrix. So memory counts easily, not easily. So system has a sort of or the enough space or the memory capacity to store and sort of or simulates sort of such kind of sort of large system. Okay, so largest sort of the matrix size we were able to handle and sort of benchmark was sort of 1 million dimension. 1 million, so matrix dimension. But of course, the memory capacity is, so we need sort of almost 10 teraflops, 100 teraflops, 1 terabyte, 10 terabyte or 100 terabytes orders are required. So we need to run such a sort of very huge ultra scale sort of benchmark diagonalizations, at least 1,000, 2,000 of the computational nodes, even the Fugaku has a sort of, yes, so Fugaku runs sort of shows very high performance. Okay, so you running this benchmark with 4,000 CPU nodes, and spend how long? You can see this competition. Yes, here, so a lot of time, so 3,000 seconds. So approximately 1 hour, so we can compute so the full eigenvalue and also the eigenvector computation. So yeah, here, so the number of the eigenvectors computed, so it is 1 million. Needed so the 3,000 seconds. So memory requirement was I cannot so translate it into the megabyte, gigabyte, but almost the terabyte or the 10 terabyte, 100 terabytes, so the order. So yeah, this is also the reasonable results because we had 30 petaflops. Yes, this benchmark. So it is almost 10% or the 50% of the theoretical so the peak performance of the Fugaku. So this is a very excellent benchmarking, but it is also it is saying that so the 1 million dimension is not also the demonstration. So it is feasible to apply the benchmark, not the benchmark, I'm sorry. This is the real the application code. So if you have a sort of enough computation time, so it is a sort of realistic sort of simulation. Okay, so so I want to stop here. So and so I want to restart the theoretical part of the eigenvalue problem. Yeah, okay, thank you.